Today is November the 15th, 2012, and today we're going to listen more likely to Stanley Fishkind, who is an electrical engineer in Baltimore, Maryland, with 40 years experience in aerospace and a broad range of aerospace, starting out in 1965 working for Westinghouse in the defense area, going on to Hopkins University, then doing some time at the Israel Ministry of Defense and consulting for many years as a scientist, and then 20 years at NASA. So Stanley, thank you for...
And then, yeah, right, okay. The reason why I said that it's really 40, it's 20 plus 20 at NASA.
Oh, okay.
So
I think what I'd like to have you talk about is your experience as an aerospace engineer, just in the big picture, about your
The biggest picture is that the technologies are always changing, usually for the best. And in my experience, I've come across older technologies, more primitive technologies, which are in many ways better than some of the newer technologies. For example, the front end of a missile. Front end of a missile gets very cold. And if you were to put into it integrated circuits and all kinds of transistorized devices, the problem is that cold really kills those kinds of devices. And with shock and vibration, they go to pot. Guess what? The Russians decided to go to flat pack vacuum tubes. So in the front end of their missiles, you bring along the heater, and since the life of a missile in flight is units of minutes, who cares? So you have a very, very robust, basic system, and it does essentially the same job, and you rely on a very mature, robust design, as opposed to having all kinds of gizmos in the front end of the business end of your missile. So if I had a choice, for example, if I'm flying to the moon or being in space, I would probably elect to choose Russian systems as opposed to American systems. Not all, but some. If you want reliability, something that really works well, that has a long track record, there's a lot to be said for Russian systems. How do you like that?
Well, I wasn't expecting you to say that, but that reminds me of the whole thing about NASA and the ballpoint pen that could write upside down, and
yes.
The Russians going with a pencil to achieve the same goal.
Exactly. The mission of NASA is a little bit different than just about any other space agency around the world. NASA does research and development and spins it off to industry. The Russians, as we've seen when they copied the designs of some of our shuttles, and the Chinese and all the others that copy our designs, they're good at copying, and they really don't necessarily have the insight into why decisions were made. However, if you can crack into their databases and get the technical briefs and the background materials, then as part of our mission to educate people in the research and development, then those who look at our stuff could probably figure out what was going on in our minds. But let me just say this. As someone who was involved in the space shuttle world, you had hundreds, thousands of people who, when they took apart, when a shuttle comes back to Earth, they essentially disassemble the whole shooting match. And you have people who have been living with these systems, looking at them, and trying to figure out why certain things are looking like they are or why they failed. So you bring real intelligence into looking at the design and trying to improve things. We have drawings and systems that go back into the 50s, 40s, 60s, 70s, 80s, people who manufactured integrated circuits, people who assembled all those good things, and you have a lot of insight. So when you don't have that insight, then you don't have that ability to figure out what's really going on. Classic case is when you have integrated circuit that was manufactured and you clean it after you solder it, you use XYZ solvents. Guess what? Sometimes when they're sealed up and they're left on the shelf for years, they start to grow whiskers. And you just wouldn't have guessed that would be the part that gave you a hard time. Whiskers start to grow inside some of these cases, and they short out, and all kinds of interesting things happen. So again, it's really, really important for you to stay ahead of the knowledge curve by keeping your corporate knowledge intact. One of the biggest problems we had with the International Space Station was it was thought that they didn't want to capitalize on the information that was generated and gathered as you went through the design process and through the design reviews. And they decided, NASA decided to cut corners where they thought they could, and there's a lot of information that was never really harvested properly. When you have a small program or a project, you want to spend a lot of time documenting what you've got and the decisions that you entered into and why you did X, Y, and Z. How's that?
That's great. You mentioned something interesting about, I guess, copying, which made me think about reverse engineering. When you were in the 70s, you were in Israel at a very interesting time during the Yom Kippur War, and you were involved with reverse engineering a SAM-6.
Yes.
Tell us about that.
That was one of the most exciting chapters of my life. I lived in Israel for about a year before the Yom Kippur War, and I was reverse engineering American computer systems. And when the war started, the first day of the war, I was making, since I was not an Israeli citizen, I started making artillery shells. And the second day of the war, I was making radar decoys. And the third day of the war, we started to bring back into our office parts of Russian surface-to-air missiles. And we were able to start to piece together the things. But the real fortune was, about the third or fourth day of the war, we actually captured a burnt-out launch control center. It was like a tank. And the only thing that was wrong with it was that 95% of it was incinerated, but the wiring harness was intact. So we started looking at it, popped it open, looked inside, and we see all these little sandwiches, phenolic sandwiches with a couple of transistors, a couple of diodes, a couple of resistors and inductors. And we soon discovered that they were able to manufacture universal modules. And depending upon how you wired up the module, you would get your Boolean function and or NOR, et cetera, et cetera. And the secret was in the wiring harness. So we were able to look at the modules that were still existing, and we found out that they were using components that were 10, 20, 30, 40% tolerance. And the way they compensated for those wide variances in tolerance was to have at the very end or in the middle, depending on where it was critical, they would have some variable components to get the timing in sync and get the amplitudes just right. So by having these universal modules, 95% of the launcher was using these universal parts, and having the resistors, capacitors, inductors at the very end or in the middle during the critical functions, you can very quickly bring up a system to be really, really effective.
You mentioned 30 to 40%.
Yeah. So, for example,
how does that compare to a Western system?
Oh, the classic is you pick up a resistor made to 1,000 ohms, and it's usually marked. It's down to 0.5%. Half a percent, 1% tolerance, and that's normal and expected. And then you get some other stuff which are fairly exotic. You get stuff which is a 0.5% tolerance. These guys, if you had a transistor or inductor or resistor, whatever, it was marked as 1,000 ohms. It could be 900 ohms to 1,100 ohms. I'm just pulling out numbers, but the idea is that you can get away with a lot of sloppiness in the implementation and just learn how to tweak it at the end or in the middle and get the right signal. Why
did you think that they designed it that way?
Easy. You don't want to rely on single manufacturers for your parts. And by using these old, there's nothing, you go in the field, you find in everybody's cubbyhole, you got all these old components, and they work. And you just rely on old existing technologies. The other part was, you don't have to have a really skilled technician to repair your system. If you're seeing that the timing system's not right in the launcher, what you would do is go in and literally throw away the 30, 40 modules, and then tell the guy to go to the bucket and bring in all these universal parts, plug them in. And since they're all universal, you don't have to worry about pre-tested stuff. It just works. And the level of intelligence or the background for your technician can be really small. So you don't have to have a really swift crew to repair and maintain your equipment.
So you could have really robust system in the field with lack of talent. Troops.
Yes. All you need is one or two smart guys who know the system and can figure it out, or a good training manual or a diagnostic manual, and you can get a thing working.
How did you know when you looked at the equipment? How did you know what you were looking at?
When
you opened up all these parts.
They were all the same. They were all 95%. In other words, the modules were as big as here, take my face watch over here. It's about 2 times that large, and they had half a dozen. They had 10, 15 leads sticking out the bottom of the phenolic sandwich, and they were all exactly the same. All exactly the same.
So when you were looking at the harnesses, was this? I mean, everything must have been in Russian, right?
Let's be real. If you're going to be manufacturing something, you manufacture with 2 sets of markings. One is the language of the manufacturer, because these are the people manufacturing, and then you mark it in English, because how many people in Swaziland know Russian? Practically zip. How many people know English? A fairly good number of people. So English is turning out to be, or at least at that time, was the dominant foreign language. And then when it came time for you to train the troops on how to use it, you had a training system, and all the systems we picked up had English training manuals.
So you looked at the equipment in '73, and you were able to take it all apart, and there was English in there, so you knew what you were doing.
Right.
So then, what did you reverse engineer?
Well, it gets into an interesting symphony of things. The Russian launchers, the missile launchers, were configured like an X. In the very center, you had the command post, and at the 4 ends, you had the launchers themselves. When it came time for the Russians to test the systems, they put around the radiating elements screens, so that when the RF was radiated, they wouldn't get beyond the screen. And then, in wartime, they obviously took off the screens and broadcast. So when the war started, we were picking up all kinds of RF intelligence. And then we married the RF intelligence with the actual equipment we have, and we saw, so here's the chirp, the homing signal that's coming in, and we correlated with the equipment, and in the span of about 3-4 days, in our digital computers, we were able to simulate the entire system, both the launchers and the missiles, and all the stuff that goes in between.
What was the outcome of that knowledge?
We were able to shut down the missiles in flight. So the SAM-6 missiles are like 3 fingers of death coming up at you. So when the pilots would see or detect those tones, then they would turn on the jamming systems, and we were able to essentially defeat the missiles as they were taking off. Either tell them abandon, shut down, turn off power, whatever it is. So the effectiveness was tremendous after the first couple of days of the war.
Do you think that was one of those winning solutions that that turned the war?
Oh, it was clear. It was a clear case. Now, while the war was being executed in the early days, since you were flying against heat-seeking missiles, what you would do is you take a long aluminum pipe and stick it on the back end of your jet engine, and because of the high temperature of the stuff coming out of the jet, the aluminum pipe would get really, really hot. And so when we had handheld surface-to-air missiles being launched, the small guys, the heat seekers would start to nibble away at the pipes that were being drawn by the airplane. So you had the engine, and you had the pipe, and the missile would come up if it was in your neighborhood, and it would home in on the hottest part up there, which would be the really hot pipe. And so after flying a mission, you get lots of nibbles of stuff coming up around your tush.
Wow. So now the interesting thing about reverse engineering that I'm thinking about based on your experience, we recently had the situation of the U.S. spy drone that
Yes.
crashed in Iran, or was brought down by the Iranians, as they say. And of course, we also have many stories around reverse engineering from the Chinese. So I guess my first question is, in terms of let's talk about re-engineering. How hard is it if you were to, let's say, get your hands on the Sentinel spy plane, or if you are the Chinese and you get your hands on some of the technology and the pieces? How hard is it to re-engineer things today?
Darn good question. It all depends on how sophisticated the components are and how enveloped they are in the system. When I was at NASA, we had security devices that we were flying on the space station so that we can get the encrypted data feeds from the ground, go to the space station, and then go through these racks of equipment, and you come to a decoding module, and then you get clear text coming out. So one of the things you want to do is bury your most sophisticated, sensitive, highly classified stuff in compounds and gook that would make it very, very hard to take apart once you had it in your hand. If you can't do that, then you have to treat it like a black box and then do all kinds of simulations and exercises. So you try to lock up the hardware and into a very sophisticated package. And you really need to have insight into what you're looking at, even though it's a black box. So you can spend a lot of time, a lot of energy probing and maybe not get it right.
So, for example, would there be reason to believe then that what the Iranians got their hands on, they don't really understand what they have if they tore it apart?
If it's an advanced technology, real advanced technology, it'd be tough. But just about anything can be cracked, intelligence-wise, after a long time. Tough question. It's a cat and mouse game between those who have and those who want, and those who want to do. Classic case we have today is hackers, taking apart your data stream and figuring out what's inside the package. You have all kinds of encryption, levels of encryption, but after a while they can crack it. It takes time, but they can get it. Now, if you're part of that technology stream where you're always improving, and using that stuff, and you just leapfrog over the technology, reprogram it maybe, you got a chance of keeping ahead. So you don't want the hardware to fall into the other person's hands. You certainly don't want the design documents, but we have a problem with the way we do business, and that is we publish everything, and we have people going to technical meetings and sharing all kinds of information. So it's a very tricky game on promoting knowledge, intelligence, insight, and protecting your goodies.
So not good news then for what happened in Iran, and that probably explains why the Chinese have been able to accelerate so much of their own development, technologically speaking, particularly in aerospace.
Oh, yeah, aerospace is just ripe for picking. I mean, if you have a large enterprise and you have a lot of work packages and a lot of manufacturers and a lot of this and that, and you want to promote communications, you're always sending design documents and technical reports and analyses and all kinds of stuff out. And it's very easy, not very easy, it's been easier, given the technology, to go in and lift the data stream and peruse the libraries. That's
interesting.
It's a reality.
So let's move on to your time at NASA.
With pleasure.
Tell me a little bit about what you did at NASA for those 20 years.
The best way to talk about NASA is that you have to understand that it's the national resource for doing research and development. And you don't know what's going to happen when you do research and development. I think the classic story is that Columbus went to the New World looking for gems and diamonds and stuff like that. And what did he do? He brought back potatoes. So, he didn't get a mission statement, bring back potatoes. He said to his sponsors, I'll bring you back gold and silver and all those kinds of riches. But as it turns out, the potatoes were really necessary for the sustainment of life in the Western world. So you never know what you're really going to find when you do research and development. So you try to have a program that is reasonably funded and wide enough in scope so that when you discover this thing, then, oh, look at that. And then you plow it back into your design. So if you look at the beginning of a program is consists of many, many projects, and they all have design cycles where you have inputs and outputs and off-ramps and places of figuring out what to do. You learn and publish as much as you can about what works and what doesn't work. And you go back and try it again and again and again. And then when it gets to the point of being good and reliable and robust and meets requirements, then you go into deployment. And then you're off to the next phase. So the name of the game in NASA is research and development and spin it off to private industry and other government institutions.
So what about the space program?
Space program. The Space Shuttle, which, if people ask you, what do you think about the space program? The thing that comes to mind is the series of space rockets, the space shuttles. They don't really remember too much about the early days when you had Mercury modules and Apollos and whatnot. NASA overreached and tried to combine too much into a very, very complicated package. The shuttle, the space shuttle, there were about 130 of them, 130 missions that went up, and we lost a couple of them. A typical shuttle consists of about 2.5 million parts. That's a lot of parts. And you want all of them to be working at top efficiency. And you know that you're going to have failures, so you build in systems that are redundant. You have 3 sensors measuring something, and then you look at the sensor outputs, and then you do a vote, and you say, all 3 of them are saying it's 100 degrees. Hey, that's great. Oh, and now you look at this, and you say, oh my gosh, I have 2 sensors. They say 100, and 1 sensor is offline. So you do a vote, 2 out of 3, and you're in business. Then if you get down to the point where 2 of your sensors are out of whack, and you only have 1, and then do you really believe it? So we had the space shuttle was built with triple redundancy as much as possible. But the problem is you really don't know what systems are going to take you down. So you have a large effort to to understand that if you were to build something that was 99.99995% good, try it again, 99.9995% good, would you risk your life on that? And the answer is yes. I don't know of anybody who would not risk their life on something that's 99.9995% good. Problem is that on the space shuttle, we knew that there are about 3,000 of components that were we call Criticality 1. If they failed, game over, loss of life, loss of mission. Well, what's the reliability of all these 3,000 Criticality 1 items? Most of the time, they're 99.999% good. Guess what? Take 99.995% to the 3,000 power, and you get 0.87. That means 87% of the time it's going to work fine. But because you have this tremendous multiplicative effect, 13% of the time you're going to meet with disaster. It's going to fail. Now, would you put your life at risk on something that was 13% guaranteed, not guaranteed, 13% chance of failure? That's a tough question. Most of the people I talk to would not put their life on the line for that. But there are people who are willing to put their life on the line, test pilots, adventurers with a chance of 13% chance of catastrophic launch. So for every single solitary launch, you had at least a 13% chance of failure with every launch. And every time we did have a failure, it was something where it was unknown unknowns. You have knowns, which you understand, like the top of an iceberg. Then you have your unknowns, and you have your unknown unknowns, stuff that's really down there in the dark, and you just don't know what's going to happen. So you have a lot of guys and gals who perspire heavily when a launch takes place. And the Space Shuttle program was an R&D effort and not an operational program. Operations means you can bank on it and go to sleep at night and be happy with it. You know, you have problems, yeah, but in R&D, you're always trying to bring the latest technology or best technology, or trying to fix problems, or refly this experiment, or do this and that. And the shuttle was a research and development effort. Problem was that it was sold to Congress in a way that they just couldn't meet the specs. It was thought that you could launch a shuttle, have its mission, come back to Earth, and refurbish it in a couple of weeks and send it back up. Well, you can't do that. You can't do that. It just, when the shuttle comes back to Earth, we take it apart and look at everything, and look at it, and look at it, and analyze it, and rebuild it, put in new parts where it's needed. So you have a huge amount of time and energy on the ground in getting it back. So you just, the timeline was just unrealistic in the way it was sold to Congress.
You still look back on the program as overall as a success?
Yes, because if you don't go there, you'll never know. And at some points, you have to be strong-willed enough to stand up and say, gentlemen, ladies and gentlemen, I'm declaring success and the program is over. And you go on to the next thing. And it became pretty clear to me after I got involved in it that I was able to stand up at meetings and decision meetings and vote no. You want to have, when you have a design review or a launch decision made or something like that, you get as many bright people in the room, experienced people in the room, and you don't want all yeses. You want to know why it won't work. And there was a change in philosophy as we went from the first shuttle disaster, where you had to a design review or a launch review, you had to stand up and say why it won't work. So if you had a feeling, or if you had data or preliminary information saying, there's a big risk, but I don't have enough time to really prove it. In the early days of the program, you were not allowed to get up and say, guys, I have a bad feeling about this, or my data is pointing in the wrong direction. They were insisting that you have a clear cut. This is why we can't launch, and I got the analysis, and I'm going to prove to you why it won't work. And in the wake of those disasters, we changed that design review philosophy and launch review design philosophy to stand up and tell me how you feel about it. And if you're convinced that it's unsafe, we stand down until we can prove that it works.
That was a big change in the culture then.
Oh, it was a night and day. It was 180 degrees difference. The change from prove to me that it will fail to prove to me that it will work. That's a whole mindset, and it took a long time for that to happen. There's a phrase that somebody coined: launches are optional, landings are mandatory. So when you have billion-dollar devices, systems, and people's lives riding on it, you want to be damn sure that you can get those people safely off, safely in orbit, and safely come down. It was a major mindset change in how we did things. And we also had a lot of people who had, I'll use the phrase, the male hormones associated with the program, the project. They just, you're up there on the ladder and you're unscrewing the light bulb, and your spouse comes over and say, honey, you're going to fall over. And you say, as a typical male, no, I'm not. I'm fine. And you just keep on reaching over. And then when your spouse says, dear, if you don't get off that ladder, I'm going to divorce you, then maybe you'll pay attention. But a lot of people I know will just continue stretching out there and doing it and prove to their spouse that they're okay. And we had a lot of guys and gals who were so married to the program that their feelings just blinded their common sense. How about that?
What you're saying, of course, is a data-driven decision invariably is going to be the better decision as opposed to an emotional.
No question about it. But a funny time in the space station, we had to decide what should we build it to, using metric or inches for for all of our designs. And we were at the very beginning of the program, so we had a very nice board meeting. And we had all kinds of people come in and present the case for metric versus inches. And this is here in the United States. So it came time for the vote to be taken, and the vote was 56-1. 56 people, organizations said metric. And there's one guy who said English, inches. Well, guess who won? The guy who had one vote. He was the program manager. So even though everybody on his team said go with metric, he said no. When I want to have a quarter-inch bolt, I want a quarter-inch bolt. I don't want to have so many millimeters and this and that, where we don't have the ability to manufacture this stuff right. And I want to have universal parts, and most of the stuff is going to be built here in the States. And all of our systems are English, American system, and that's the way it's going to be, even though it was an international program. So you had to do all kinds of interesting mating adapters to go from the American-made stuff to European-made stuff, and you had to agree to the interface. And that was always a fun task, to make it work on one side, make it work on the other side, but then you had to expend a lot of time, energy, money, weight, and power to keep the interface just right. the mechanical devices.
If we look forward, do you think that NASA should continue to try and figure out or have a role in manned spaceflight?
Oh, they're the only game in town. The only game in town.
I mean, what's the point of all the research?
Oh, very simple. You don't know. Let's say you're going to fly to Mars. Make up a number. It's going to take you 3 years. And then you're flying in through space, and you're experiencing microgravity, very low gravity. Well, guess what? When you're in a microgravity situation, you lose 1% of your calcium each month. 10 months, you lose 10%. Okay? So after 3 years of mission, when you land on Mars, all of your bones are going to be so brittle and so cracked, you're going to have people just breaking their bones just as walking around on the surface of Mars. How are you going to do that? Tough question. Well, one way of doing it would be to maintain 1G on your space vehicle. Okay, that works. 6 months into your flight, Johnny gets really sick, and he needs a doctor. He might even need an operation. Well, how do you equip your medicine case for that? You bring along 1 of every drug, 3 of every drug, or maybe you learn how to manufacture what you need in space. Suppose you need an operation in space. You tell the guy, tough it out for 3 years. No. What you do is learn how to do telemedicine, where you have the ability to do remote operations robotically. So, you might not get a lot of great feelings from the crew member who has to have his appendix taken out by this robot, but, we should be able to learn how to do our medical procedures, our operations robotically, so we have a really smart operator at one end and reliable stuff at the other end delivering the care. So getting there, you have to solve all kinds of problems. Let's talk about crew makeup. 10 people going to Mars, okay? 10 guys? Nah. 10 women? Nah. 9 men? 1 woman? 2 women? 8 guys? The mix is interesting. And then how do you take care of the problems of those people who become unhinged in the middle of their launch or in the middle of their mission? We had that on some joint Russian-American missions where somebody starts to lose it. So what do you do?
Well, what do you mean lose it?
Become irrational or neurotic, or they lose medical competency.
Right.
So how do you deal with that? Well, learning how to deal with those things gives you an insight on what to do when you're into submarines, for example. Your mission is to be under the North Pole for 6 months. You can't come up, or you shouldn't come up. And what do you do when you have a problem with a crew member? So just start to expand it. So getting there is half the fun. That's the research and development part. I mean, you have questions about psychology and physiology and medicine and food, and the list goes on and on and on.
It sounds like you're making a very good case for unmanned programs.
Oh, it's a classic. There's a Marshall approach, and there's the Johnson's approach. The Johnson Space Flight Center in Houston, and the Marshall Space Flight Center in Huntsville, Alabama. The argument can be best made by saying you can send robots to those places that you need to go to, and you learn without having to worry about solar rays and high-energy particles going through your system, messing up your DNA. But then the other side of the coin is that when you're out there in the environment, what a human being can see in a minute or a few seconds can't equal the experience you get from the robot. So it's a very interesting tug of war on how do you want to approach it. So you come up with a philosophy that says you first send the robot out there and you do your exploration and then you learn, and then you follow up with human exploration. But it's an interesting tug between those two, and at least NASA is aware of those two different philosophies. And sometimes you have a program manager who's switched out because he comes from the human engineering side and the robotic side. So you take the best of both worlds.
Do you think that NASA will ever go back to manned flight? I mean, they've got a very successful program now with the Mars rover. I mean,
Americans spend about, I forget the number, $10 billion a year on potato chips. That's almost the cost of the NASA space program. And what you're getting for your potato chips, the cost of potato chips, is you're getting world-class science. You're getting world-class research and development. You are changing the astronomy, the physics, electronic. You're changing your knowledge base every single day, and you're opening up more and more and more. So, it's a research and development opportunity that you can't afford to pass up, rather. It's who else in the world is doing world-class research and development? And you never know what you're going to find when you do research and development. You'll always get results, and it might not be the initial thing that you look for, but the byproducts might turn out to be the thing that this helps me in A, B, C, and it wasn't X, Y, Z that I was looking for.
If you look back over NASA, if I as a taxpayer was looking back over the years of NASA, what are the things that you could point to and say, here are manifest examples of value for money?
Oh my gosh.
Give me the top 5.
Oh. The first thing people would say would be...
not Velcro, please.
No, not Velcro, and Tang. No, but for example, satellite communications. Before, we used to have ships in the ocean tracking probes that would be zipping around the world, and you'd have maybe 3, 5, 10 minutes of exposure time, and that was good. But we figured out that what you really needed would be remote satellites, geostationary satellites up there that could see. 3 satellites could see the entire world. And so we developed a telemetry data resource system, TDRSS, that allows you to have a satellite in continuous view of 3 geostationary satellites and bringing down data. So that was a major, major, major change.
GPS.
GPS was a DoD development, and as it got deployed more and more, it got to the commercial air market. The biggest problems you had with airplanes was they were always crashing into mountains that you didn't know were out there. So NASA had a number of missions on the space shuttle where we mapped all of the, not all, but 95, 99% of the world topology to some degree of high resolution. So we had missions flying around and mapped out all the mountains and the valleys all around the world, and that now gives you a greater degree of confidence when you get into the airplane. You have to fly with GPS, and you have a good database on where you're at and where you're not. It improves your quality of life here on Earth. So, cell phones, golly bumps, 20, 30, 40, 50 years ago, you couldn't even think of a cell phone. But we needed to have the ability to do communications. And then you get into search and rescue. You have a little beacon on your little dinghy that goes off, says that you're sinking. And you now have...
That's a NASA technology?
Yeah, research, yeah. It's what's it called? Oh, I forget what it's called. It's search and rescue. Mm-hmm. But what you have is a beacon that would go off when you're going down or in trouble. And we have satellite systems, American, Russian, Chinese, Indian, that are always out there listening for those kinds of data. And then when you get a distress signal, it comes in, it gets parsed out and figure out where you're at. So here is saving lives. And again, it's a result of international cooperation and sharing technology. I used to be a chairman of some, I'll call them international trade groups. So for example, I have, as America, I have 15 sites around the United States, around the world that I have. The Europeans would have another couple dozen, the Australians would have this, and the Chileans would have this and that. And we have space probes, so what we do is try to figure out ways to trade assets. In other words, here's a satellite going around the world, it takes about 100 minutes to go around, and because of geography and mission profile, the best you can do is maybe 20 minutes over the United States, but then you've got the other 80 minutes, where are they? Well, they're over Chile or over Australia, over India or whatever. So those space assets can be brought in to listen into your satellites. So I'll tell you what, I'll trade you 10 minutes of contact time for 10 minutes of your system. And we work it out, and we're sending each other's data. And that way you don't have to build up huge infrastructures on the Earth to do it. And the other way, of course, is doing geosynchronous satellite communications, where you're always in view of your own human system, your own national system. So there's, I don't remember the numbers. I used to have a huge file on all the benefits of NASA's research and development, but it's a huge investment, huge payoff.
Last item we can talk about then.
One is more I want to talk about.
Looking forward, where do you see, if the government doesn't sponsor, Congress doesn't give NASA the kind of resources like your 10 billion number, what happens?
Well, the way we built the Space Station program was we had work packages in every state of the Union. So you have one place building rocket motors, another place building toilet systems, another place making shells, and we had the work packages all around the country. And you give each of those work packages money.
So each congressman's got a stake in the game.
That's right. Let's be blunt about it. That's the way politics work. You get your work packages out there as diverse as possible. And then nobody can ding you on the results of research and development.
I'm sorry, the cynic in me makes me think now NASA's one giant pork program.
If you're doing useless stuff, if you have a bridge to nowhere, then I could say that. But what we're talking about is psychology, physiology, chemistry, electronics. Yeah, the list goes on and on and on. And people, are looking for those places to dream and envision, and do great stuff. And if you have a country that suspends that, then you lose your dreamers. And where are you? You're just like any other grubbing third world, tribe that's just trying to keep alive. So yes, it's research and development. It's a luxury, but it's really a necessity because it's going to keep you alive and well and healthy.
Thank you, Stanley.
My pleasure. Come again.